This is StarTalk Special Edition. Neil deGrasse Tyson, your personal astrophysicist. I got Chuck Nice with me. Chuck, baby, how you doing?
Hey, Neil, what's happening?
I heard you had something neat in you. What's that?
All the Oppenheimer craze is happening right now. And, you know, when you get down to the science of that, you're talking about fission and fusion. Now, you know, so what is the difference between fission and fusion?
So the periodic table is a sequence of nuclear count of protons. From hydrogen, which has 1 proton, helium, 2 protons, lithium, 3 protons.
Right.
You just count them up all the way, and you keep going. Okay. It turns out the nuclei of atoms store energy. That's not much different, philosophically, from molecules storing energy.
Right.
So, gasoline molecule stores energy. It's just sitting there as this liquid, minding its own business. Yep. Wait, you take a match, you release the energy that was in the molecule. So this idea that there's energy to be released in the atom, that's not so weird when you think about it.
Right, right.
Okay? So the question is, how do you get access to this energy? Out of the atom. What we learned slowly in the late 1800s and early 1900s, that some atoms are not stable. A version of uranium is not stable. When I say a version, it's one that has a different number of neutrons in the nucleus. But it's still uranium because it has 92 protons in the nucleus. All right? So you can vary the number of neutrons, and those are called isotopes. Mm-hmm. An isotope is the same atom, but different numbers of neutrons in the nucleus. When you do that, they have slightly different properties.
Right.
So there's a version of uranium that spontaneously breaks into 2 other atoms and releases energy. So that's what we call radioactivity. If an element is radioactive, it is splitting on its own and releasing energy, and the thing that it's in will start feeling hot.
Oh.
Okay? So that splitting of an atom is called fission.
Okay.
Fission. Now let's go to the low end. I can't break hydrogen, it's only 1 proton. When you're at the low end, you can cram the elements together so that they make a heavier element.
Uh-huh.
When you do that, the mass of the heavier element is less than the sum of the parts. Where did the mass go?
It must have been released as energy.
According to whose equation?
Einstein E equals mc squared.
There you go. Energy and mass are equivalent. If you lose mass through this phenomenon, you gain energy out the other side of the equation. So, I take 4 hydrogen atoms, cram them together to make a full-blooded helium atom, which has 2 protons and 2 neutrons. Why doesn't it have 4 protons? 2 of the protons turned into neutrons spontaneously.
Look at that.
That's what they did. Oh, now wait a minute. Didn't they have a positive charge? And now you have a neutron that has like no charge? What happened to the charge? Did it just disappear? What happened? Nope. The budgets are kept clean in the accounting ledgers of particle physics. So, a positive charge was retained by the emission of a positron, the antimatter version of an electron. So, a proton becomes a neutron and a positron. Now, a positron is antimatter. So, if you're antimatter, you are leading a very risky life in a universe of matter. Because if you encounter an electron, you annihilate and become pure energy.
Right.
So not only does the nucleus release energy, because the mass, it has less mass, the 2 protons and 2 neutrons, you also get energy from the annihilation of the positron. Okay, so make a long story simple. You can take light atoms, cram them together,
Right.
make heavier atoms, and energy gets released. You can combine hydrogen to get helium. You can combine helium to get carbon. So that is called thermo. It takes high energy to do this. Nuclear, nucleus of an atom. Fusion, you're bringing them together. Thermonuclear fusion. Light elements become heavier. Our sun does that
That's what our
every
sun
moment
does.
of every day. It converts hydrogen into helium, releasing energy, bathing us in warmth. At the high end, you split atoms and they release energy. Okay? You want to make a weapon that taps the energy of the nucleus. Okay? Well, it takes very high temperature to fuse hydrogen. The sun does it under high temperature and high pressure.
Right.
Meanwhile, uranium is falling apart for free. So it turns out when uranium unstably splits, it releases a neutron. Well, wait a minute. Here's something interesting. If it splits, did I wait around for the next atom to split? Or can I force a split? It turns out, if you do the equation, one splitting atom releasing a neutron can split another atom. So if you split two, if two neutrons come out, that'll get split and it's dense enough. You don't want it escaping. The material has to be dense enough so you guarantee it's going to hit another atom. Split that, and it goes from 1 to 2 to 4 to 8 to 16, and you get a runaway chain reaction. And if you purify your isotope of uranium, you cram it down, and you initiate that with a trigger, you have an atomic bomb.
So you're looking at a tremendous release of energy.
Yes. So you can get a certain amount of energy out of that, and it takes effort to purify the uranium. All right, because you need a uranium mine, and you got to make sure there's just that one isotope, because only that one isotope will do this, not the other ones. This is why you use centrifuges, because one isotope is slightly more massive than the other, and so you centrifuge it, and the heavier isotope goes to the bottom, and the lighter ones go to the top. Then you skim off the top, centrifuge it again, and it becomes purer and purer and purer. Did you see Top Gun Maverick?
No.
The main point of the film, Top Gun Maverick, is they have to take out this underground bunker that's purifying uranium. There's only one reason to do that, because you're going to make a bomb with it. There's no other reason to have purified, fissionable uranium. Okay.
Right. So what is more powerful, fission or fusion?
It turns out a fusion bomb, which is what the sun does, can become way more. You can make bombs of different sizes, but sky's the limit practically with a fusion bomb. Okay, starting with hydrogen, and hydrogen goes to helium, but you need it has to be small enough, and again, it has to be able to be self-driven once you start it. Okay, so the bombs that were dropped over Hiroshima and Nagasaki were 10, 20-ish kilotons of TNT. In fusion bombs, which came later, those were not perfected until like the late 40s, early 50s, when we were working on them and finally tested them. Those are capable of megatons of power. So instead of kilotons, you have megatons, 1,000 times more powerful. Because apparently one bomb leveling a city was not powerful enough in the Cold War. And so that's why they say the 20th century was the century of the physicist, because the Cold War defined geopolitics, and the Cold War came about because of the handiwork of physicists combined with engineers to actually make the bomb. And so, yeah, there's a nuclear bomb will not only ignite the pulse of energy is enough to sort of incinerate whatever is in a sight line to it. But then there's the blast wave that'll completely level anything that happens after that. Because the pulse happens at the speed of light, the blast wave moves at the speed of sound, which is slower. So if you're not incinerated, the blast wave will take you out. And one of the concerns about, you want to talk about climate change, is if you target a city, it's one thing if you target forests. Well, then you incinerate the forests, and that'll put soot into the air, wreaking havoc with our climate. If you do it over cities, let's take LA, for example, where there's all these freeways. If the freeways are made of asphalt, if it's possible for the asphalt to catch fire.
Yes.
You want to talk about further disrupting the climate. I know if you were where the blast wave was, you're not really concerned about the climate. You're concerned about whether you were vaporized or not. But the rest of the world would then feel this. So this is, it's an extraordinary power that we wield. And we rapidly realized we needed some way to regulate it. So we had these test ban treaties and this sort of thing.
Right.
And early in this, they did a calculation. They said, if we set off a chain reaction in this bomb, will that chain reaction continue into our atmosphere? Because the water molecules in the atmosphere, there's hydrogen in the water molecules, there's hydrogen in the oceans. Okay? Would this start a chain reaction and completely incinerate our atmosphere and our oceans? So you can do a calculation and show that it's not likely. Every calculation has a statistic, especially in quantum physics, there's a statistical probability that could be vanishingly small, but if you're honest, you'd report that even though it's vanishingly small. Part of the problem is, in order to have this runaway fusion, you need the concentration of materials for that to happen. And you don't get that in the oceans.
The atmosphere or the oceans, right?
Right. That's part of the problem. It's all the energy that comes out of E equals mc squared.
Yeah.
And Einstein himself, he sent a letter to Roosevelt saying, I think the Nazis are working on this. We should too. Okay?
Nice.
Then we start the Manhattan Project. But then he realized maybe, this is not a good thing. All right? Plus, we learned that the Nazis were not really close to it. That was an occasion to say, okay, we're done here. Let's resort to conventional weapons. And we didn't. We pursued it.
Wow.
The frontier of physics.
The day has to arrive in all of our lives when you want to be in arm's reach of a fusion expert.
Fatima Ebrahimi.
You have a PhD in plasma physics. That's a whole thing. And you're a research scientist at the Princeton Plasma Physics Laboratory, PPPL,
Correct.
out there in Princeton, New Jersey.
Yes.
I got with me Paul Mercurio. Paul.
What's up?
So this is, people have heard fusion, they've heard the word, and they've heard the word plasma, and most people think blood plasma.
Yes.
This is a completely different plasma, right? Blood plasma is like what's left over in your body.
Right.
I mean, after you take out the red blood cells, I
Right,
think.
exactly.
Yeah. So this is not that at all.
Right.
Let's
Oh,
start
yes.
off, get the vocabulary on the table. What is a plasma?
So plasma is the fourth state of matter, and it's 99% of observable universe is plasma.
So it's really the first state of matter.
It's unstable.
No, not necessarily. It's actually, we are all floating in a plasma state in our universe. And if you want to see what actually plasma is when, electrons are kind of freely moving and charged particles, negative charged particles, ions, positive charged particles. It's basically a soup of, charged particles, this plasma.
All right. So why is it that we always, in physics, we see plasma joined together with the word fusion? Why are they relevant to each other?
Because our sun that actually produces a lot of energy is through fusion energy, and that's is in a plasma state.
So plasma, in order to get a plasma, it has to be very hot.
Yes.
Another thing is a cold plasma, is there?
Yes, actually, for the case of fusion, it has to be 100 million degrees to
100 million
actually
degrees.
achieve fusion. But plasmas, they could have variety. You have temperature. It could be low temperature plasmas.
Oh, but then you're not gonna have fusion.
Exactly. You don't have. Plasmas could also be lightning strikes. That's plasma. Yes.
So I remember this not a toy, this thing you could buy. One of them was this ball. That it had this sort of glowing thing in it, and you put your hand on the ball, and it would react to your hand touching the surface.
Exactly, because it's charged particles, all of these, the plasma kind of
It makes the gas, it makes it glow.
Exactly, glow, because particles could also can de-excite and kind of produce photons and lights and things.
Okay, so the electrons recombine.
Exactly.
And every time they recombine, they give off light.
Exactly.
Right,
Excite and recombine and de-excite, and you get the light.
So that's a plasma that's not at very high temperature.
Exactly.
Right, exactly.
Yes.
Okay. It was just
like
it
a
was
candle is also a plasma, but
Or the flame.
It's a flame.
The flame,
yes,
yeah.
the flame of a candle is
All right, so now you need high temperature for fusion.
Yes.
What are you fusing?
It's actually required for fusion. High temperature is required to fuse really light atoms, hydrogen,
Yeah.
and also isotope of hydrogen, heavier hydrogen, deuterium, and a little bit heavier tritium, with having two actually neutrons. So they can collide and they can fuse, and it has to be really, really high temperature to be able to kind of overcome, these forces and create a lot of energy through neutrons.
So the forces are because you have a positively charged proton over here and another positively charged proton over here. Like charges repel.
Right.
Exactly.
They don't want to get together.
Right.
Yes.
And you're trying to overcome this
exactly
with
That's
high
nuclear.
temperature.
Yes.
Because high temperature means higher speeds
Yes.
within the soup.
And you're
Yes.
able to achieve the high temperatures.
Actually, you can get very high temperature.
But are we there yet?
Yes. Actually, in the experiments or facilities that we have to create, high temperature plasmas to get to fusion, we really get to high temperatures. The temperature we actually achieve in a fusion experiments is even hotter, than the center of the sun.
Yeah, center sun's like 10 million degrees, something like that.
Yes, this is 100 million degrees.
What do you generate? What are you using?
They're trying to make another star. So how do you get high temperature? In order to make the plasma high temperature, something else has to be at a higher temperature than it. Is that right?
You get the high temperature because plasmas, carry electrons and current, electricity current. So therefore, they can get to very high speed and high temperature. So the question is that, so you get this soup, where it's going to go? So how do you confine it?
If it's 100 million degrees, what are you putting it in to contain it, to control it?
To control it is put a lot of energy through magnets.
Wait, so a magnetic field is
Yeah.
not a physical thing, so you
Yeah.
can't melt that,
Right.
Yes.
right? And all your charged particles, they respond to magnetic field, electromagnetism.
Therefore, our universe is electromagnetic force, yes, that is long range. It's one of the fundamental forces, electromagnetic forces everywhere, our sun, all the stars, wherever you have plasma, you have electromagnetic forces, and they respond to it. So you have the gas, you need to make the state of plasma, which means that you can have some waves going into the gas, like antennas, and create your plasma. You could induce inductively current into your particles, plasmas. It can go around your chamber, which we are talking about a tokamak chamber, a donut-shaped chamber. So
A
Tokamak.
yeah.
Right, because Princeton has a tokamak.
Yes.
What does that word even mean?
Two Russian scientists called this configuration
Toko and Mac. Okay, so I did not know that. It's named for actual scientists. Very
So when
good.
you
No,
say
it's not
this
actual scientists. The two scientists actually called it. It's kind of their invention, tokamak.
So when you say this chamber,
yes,
the chamber is basically sort of harnessing or controlling the plasma.
That's the donut
Yes,
shape.
the
That's
donut shape,
that is
exactly.
being heated up at incredible temperatures.
Exactly. Various ways of heating the gas become plasma and heating the plasma to really, really high temperature.
But are we
Yes.
heating it to the point where we're at the cusp of being able to use nuclear fusion and get nuclear fusion that then propel
Yes,
rockets through space much more quickly?
The rocket is a plasma propulsion.
Mm.
You actually get rid of the plasma you make from the back of the rocket. You're not confining it with magnetic field.
So the plasma rockets don't use fusion.
Not necessarily, they don't have to use fusion. But
Right.
if you that in space, we don't have any power or there is no gas station. The only thing we have is our sun sitting there, and it's only going to give some amount of energy. So if you want to go far, you need energy and you need fusion. If you're going to go stay around with solar panels, you have enough energy to use locally.
Yeah.
You could use that for just propulsion.
I remembered reading, because I know enough to know that in any gas, at any temperature,
Yes.
not all particles are moving at the same speed. Some are slow,
Yeah,
some are fast.
yeah.
The temperature is the average speed that everybody's moving.
Mhm.
All right. I remembered that there's some method where you can pick off the fastest moving particles and put them over here, and their average temperature is going to be higher than where they came from.
Here we go.
Cherry picking the fastest moving particles. Is that a thing? Am I remembering that correctly?
Conventionally, it's usually a collective, heating. It's basically you have through current, it's like current. Now, plasma also carry current. Current itself can heat,
Yeah, okay.
Really, it can actually, it's basically ohmic heating. That's one way of heating the plasma.
So that heats up internally.
Yes.
It's not hotter on the outside. You make it hot on the inside.
That's a conventional way of actually heating up the plasma, the first way to do it.
I spent 10 years at Princeton.
Yes.
In my day at Princeton,
Yes.
every year there was talk of people saying, we're almost there by producing more energy than we put in, which would then make it an energy source for the world, a very inexpensive energy source, using readily available ingredients like hydrogen, which you will find at your neighborhood water molecule. They would say, oh, it's just 5 years away. And that was 30 years ago.
Yes.
So what's going on?
You're almost there.
Princeton has a tokamak,
Yes.
but Lawrence Livermore has a different
Yes.
configuration.
So there are two approaches. One is just tokamak. Actually, Princeton has a special tokamak. It's called a spherical tokamak, which is kind of not like a donut. It's like a fat donut or cord apple.
How is that different than a standard tokamak?
The nice thing is that it's more compact.
Oh, okay.
So that's another difference. So it's a tokamak, but a spherical tokamak, and it's very special because of compactness and other things. And so by using magnetic field, you actually confine the plasma.
Okay, so there's that. So now let's go to Lawrence Livermore in Livermore, California.
It's so-called inertial confinement, means that by shooting lasers and at very small, dense target, you get fusion. So our plasma at PPPL, Princeton Plasma Physics Lab, is not that dense, but we have very high temperature. And so there's something we call a little bit specific, something called Lawson criteria, which is basically the multiplication of the confinement time, how hot you get, your density. So each
all of that combined.
And if it's larger than something, you say that, I achieved fusion. So inertial confinement has, more
generates a denser. So
denser, exactly.
Of all of those factors, is density the most important thing that gets you to?
The sun gets high density for free
Yes,
because you're in the
high
center of the freaking
density.
sun.
Yes,
It's
yes.
dense there.
Right.
So so they get free density.
But what you're generating at PPL is not as dense. So
Yes, it's
sort of like it's what I would get
confined,
at Walmart versus
Yeah.
Saks.
So you can have it dense but not hot, or hot but not dense.
Exactly.
And some combination of those two
Yeah.
will get you the fusion.
Yes.
Do we
and
know the
time
optimum
scale,
point?
Yeah.
Do you know the optimum?
We know the optimum is that you want to, first of all, fusion was achieved around 1995.
But I have to correct that. Fusion was achieved like in 1947. It was just uncontrolled, and we called it a bomb.
The controlled fusion was done at Princeton Plasma Physics Lab in the device called TFDR, test fusion reactor. It was obtained
Achieved.
achieved.
Yes.
It was we obtained fusion. It was achieved in the 90s here at Princeton Plasma Physics Lab, and also at another experiment jet in Europe later. So and about 10 million joule energy was or 10 megawatt, million watt power was obtained. So we've got fusion.
1 joule per second is 1 watt.
Yes.
Okay.
Yes.
Okay,
So
so
10
she's thinking joules in energy,
Yeah.
but watts is a power.
Watt is the correct one. It's
Okay.
10 megawatt. And actually the record is 17 megawatt later. So it's around that much.
But I have a question. You have this big fat donut,
Yes.
all right, and the whole thing is plasma.
Yeah.
But if you hit the fusion threshold,
Yeah.
does the whole thing undergo fusion? Because in Lawrence Livermore, they know if it's going to happen, it's going to happen in that little pocket that they created.
Basically, in the vessel, in the core of the vessel. So it's kind of your plasma, it's in the core. It actually needs to finally touch the wall, and that's where you actually get the energy.
It's touching it's touching the magnetic field around.
Actually, there's a real wall. It's magnetic field all around. We call it blanket.
But what forms the blanket? In all seriousness, like what creates the wall? How does that work?
It's a various solution for wall. You know, it could be tungsten.
But does it come as a byproduct?
It's a various material.
It's a byproduct of the way you're manipulating the plasma. A wall creates out of that.
No.
Actually, no. You actually put it's a physical wall.
So why is it only measured when it touches the wall?
Because it's not measured. It's actually the plasma heat is being measured in the core.
Yes.
Yes, and that's when you get really hot plasma.
So what do you need the wall for?
Because it has to be confined, and the plasma needs to meet some boundary.
Well, we thought that was the magnetic field.
Right. Isn't that the magnetic field?
So the magnetic field is all around the torus, all around the donut.
So the magnetic field gives it a shape.
Yes, exactly. Give it a shape. So you could put direct magnets around your vessel, or you actually put coils that goes around your vessel, and then the wall, and then the plasma.
Have these magnetic fields. We've all played with iron filings and magnets, and you can see magnetic field lines, and they form these loops, these toroidal loops. Okay. I know that on the surface of the sun, because it doesn't rotate as a solid object, there are these magnetic fields in there that get stretched as the sun rotates its equator faster than other regions. And there are points where the magnetic fields snap. They break, and then they reconnect. Does that happen in your space?
Yes, it happens on the surface of the sun, exactly the way you said. Sun actually, as you correctly mentioned, it's in a plasma state, also create, fusion energy. So a lot of energy in there. Another thing sun creates is magnetic field. All the motions of the plasma there creates magnetic field. So I'm creating magnetic fields. I need to get rid of this magnetic field somehow. These invisible field lines that I'm creating. Where does it go? It goes to the surface, and it kind of goes up like loops. And then the loops kind of, at some point, these invisible field lines, one go up, one go down, and then they snap. They kind of cancel each other.
Right.
And then we call it detachment. The whole loop kind of get away.
And it's chaotic, right?
Yes or no. It could be places that is really chaotic, but also it could be like a collective, ropes of magnetic field. They come together. They kind of cancel each other magnetic field, and then you get the reconnection site, and then the whole thing detached. The plasma and the magnetic field.
This is how you know that physics do this, not astronomers, because the people who study that are called magnetohydrodynamicists. Let's get back to the energy, and then I want to go to rockets.
Yes.
So if you're going to be useful to anybody, you can't just make energy under the ground in Princeton, New Jersey. It's got to be, I don't want to call it portable, but it's got to be scalable. Yes. So you can move it to a town that can generate energy that has no radioactive byproducts. You can generate it 24/7, and you're just using hydrogen.
Yes.
Whose method will be better for this? The inertial confinement from Lawrence Livermore, or the tokamak design from Princeton and other places?
You have to pursue all the methods. Other methods, we call this some more innovative alternate method, but again, using magnetic field, to kind of confine plasma and get fusion energy. So all of them need to prepare, but all of them need to get to some condition, and the condition is that you produce more energy than you put in.
Otherwise, what's the point?
We haven't got there engineering-wise. Physics-wise, scientifically, maybe in some range we can say that, we got energy from fusion. And as I said, this happened also in the 90s, at PPPL.
Yeah, there's a little bit of a overstatement about the Livermore experiment because that one had net extra energy from the experiment. And so it was championed. But the extra energy they got was relative to the energy that they put in this little spot. It didn't add up. The whole system that made the thing a thing to begin with. So it wasn't the total energy budget of the experiment. It was just the energy budget of the
local
vessel.
around the target. Yeah.
On the
And
target.
it had to be attached to that target or near that target to be an
Yeah, and that's how they make the measurements. So I think, correct me if I'm wrong, if you're going to scale that, presumably you get some good engineers in there to say, how do we make this littler and you can make this more efficient and then you just run the energy
You
out the other
actually need
side.
to also make better lasers, more efficient lasers, because the efficiency of it is not too great.
Because you have to put energy in the lasers to make the
because
energy.
the lasers are going to help you to
So you
get
need
the
engineers
fusion. Exactly. So engineering net gain is not too high in that experiment.
But the
And
physics gain
but
was
the
good.
physics gain was good. And also the physics gain is also for magnetic confinement. We have good gain before, and we are actually moving toward it with various, configuration.
Okay.
Yeah.
In all
Very
of
good.
this, the idea of excited particles, and where does that fit into all of this? And sort of how do you calm down an excited particle? Jazz music? I don't know. Candles, scented candles. Like how do you?
You asking her how does she cool down the plasma? Is that what you're
in
asking?
a sense, right?
Because the whole
This
plasma is
concept-
excited particles.
Right, but there's specific things that you do to control the excited particles.
Oh, yes, yes. I think that you just want the whole hot, plasma confined, controlled and self-heated, because it kind of interestingly, if it gets to some temperature, it can kind of on its own can get, heated the plasma for a long, long time and produce a lot of energy. And that is fusion, a system or reactor. And we have made a lot of progress in each, part of it.
How many years from now can I plug in my wall and the energy on the other side of that plug is fusion?
I mean, you know that like diesel engines, lots of, advancement. So it all takes decades, yes? And fusion it's a new physics frontiers, the whole plasma physics. When an experiment, is run, you kind of get into the new regime.
Because when you're doing actual research,
Yeah.
you're on a frontier.
Right.
Yeah.
You're not.
Well, I was
you're
just thinking
stepping
that.
where no one has stepped before.
Yes.
So you're going to discover new
So
things.
you're going to discover,
Exactly.
and you're going to discover hurdles that you could not have predicted. Seriously,
Yeah.
right? So
Yes,
in other
exactly.
words, so
Yeah.
I mean that's the issue, right?
Yes,
It's
you
like-
get into new regime, you discover new things, and the whole rocket system, it was, a discovery through in a fusion system.
Do we have
Yeah,
any
yeah.
practical application of fusion right now in any capacity that
Bombs.
other than bombs?
In a shorter time scale, we do not have to have a large scale fusion system to kind of give electricity to a whole city. We could have compact design for taking, for space.
Right now and forever,
Yeah.
as long as we've had rockets,
Yeah.
we've been using what we call chemical fuels,
Yeah.
which means they're molecules that have energy
Yeah.
contained within them. And you break apart the molecule, the energy escapes, and that is our energy source. And so that has not advanced in 100 years. Solid rocket boosters, that's a different propulsion chemical than the big
But
tank.
essentially the same concept.
It's the same concept.
Yeah.
And so tell me about plasma rockets, because there's a lot written about it.
Yeah.
And we're not even talking about fusion yet. We're just
Yeah.
keeping in your plasma universe.
Yes.
Tell me.
Plasma propulsion is basically we are talking about the next generation of rockets, specifically plasma rockets.
And they're highly efficient, yes?
Yes, they are highly efficient. In terms of, so there are several things about them is that the exhaust velocity is really high.
What's hard for people to see, just being Earth surface dwellers,
Yeah.
because you say, if I want to go forward, I just have to run or step on the gas. You're doing that at the expense of Earth beneath your feet. So the only reason why you can go forward is because Earth you're putting friction between your foot on the Earth and you're changing the rotation of the Earth slightly.
You're pushing back.
You're pushing back on
right.
it. You have something to push back on.
Right. So this is
in
your-
space.
You have nothing.
You got nothing to push back on. So the only way you can change your speed is to give something up.
And what are we giving up?
Mass.
And in this case, it's just you create the plasma or plasmoid through the process of like solar flares, magnetic reconnection. And you continuously detach these plasma from the back of the rocket and at high velocity.
Because it's at high temperature.
And
at high temperature, you get high speed.
Yes, high speed. And the rocket is being propelled forward. And it's not, it doesn't have to be high temperature. The interesting about the magnetic reconnection is that magnetic energy is being converted to kinetic energy. So it's all magnetic, yes? It's like the solar. Doesn't have to be.
So this is like, you want to get from point A to point B with this. You snap your fingers, you're there. It's like badass.
No. It's different because the particle comes out the back and the rocket recoils from it. But by how much? It's efficient, but it's a tiny mass at high speed.
Yes,
and I have a high mass thing on the other side that can only then go forward at low speed.
Yes,
right?
yes.
So how am I going to get anywhere?
You're going to get anywhere by kind of having high thrust, high force. And that is through, again, exhaust velocity. You get it. And it's constantly, you're kind of pushing it, it's like a constant acceleration. You get somewhere in a space. It's different from,
Right. So you wouldn't use plasma rockets to launch.
No.
Because they don't have that much, you can't send out that much mass. Because anytime you see a rocket, this is coming out.
So you've got to
This comes out and it goes the other way.
Use rocket fuel to get it there.
To get it there.
And
then through empty
so we're
space.
talking about like some in crazy, this is sort of like a massive Wi-Fi spot that's like got incredible power. Is that what this plasma thing, where we're going with this?
Well, I think from what I've read, but you're in the middle of it, so just correct me if I'm wrong. When you're in free space, in open space, and then you turn on your plasma rocket, it's like one particle at a time. And so you slowly accelerate. But acceleration is a constant, in this case, increase in your velocity.
Yeah, there's resistance coming on the rocket.
No, there's no resistance out there. It's a recoil, right? But since it's constant, and you do it for a long time, you can reach very high speeds.
Exactly.
How fast can you go?
Based on the results that we have, and we are actually building a tabletop prototype, you can get to 100, 500 kilometers per second. So it's still...
So that rocket can move at that speed.
But you need to get to that speed, if you go to the moon, you don't need that much of a speed. And you could do it with this plasmoid rocket. You can do, small payloads in 3 weeks or something with this plasma rocket. And it's not that this is sci-fi. No, this is actually for real because we do plasma propulsion with just electric field. Now we are doing magnetic, using electromagnetic field, using magnetic reconnection.
But 3 weeks is a long time. And astronauts, Apollo, they got there in 3 days.
Yeah.
But we're doing the fast, it's efficient.
Efficient.
It's efficient. It means that you go back and forth. It's not expensive. The fuel, it's flexible. You could use really hydrogen, the one that we want to use for fusion. Use really light atoms, so it's efficient. So it's fuel flexible and it's efficient.
Okay, so this would be the delivery vessel for supplies.
Exactly.
Because you can just plan ahead, send it 3 weeks in advance, and then we get there quickly. And supplies are very heavy, right? But you'll get there.
We're using this plasma technology to get the supplies there.
Well, I think the point is, because you're just sending these very low mass particles, though they're traveling high speeds, the recoil is small but real and measurable, and it accumulates. So I bet if we were to fly humans with one of these rockets, it would only make sense if we were going to like Pluto or something, or to the nearest star.
Yeah, then you need to use this plasmoid propulsion, you need nuclear energy, fusion or some kind of a battery to kind of give you both force, the thrust, yet you need like the
But can you control it? So if you're approaching a planet's atmosphere, can you control?
Yes, because
otherwise, are you just driving that rocket right through the center of
Well,
that?
that's a big problem in space travel because if you can accelerate and you want to land somewhere, so what you have to do is like, flip the ship around and then have it send out particles the other way. So then it's a negative acceleration, a deceleration.
Right.
And so that eats up some of your plan. But might we use this going to Mars, do you think?
Yes, because of it's because of efficiency. You could use chemical rockets if you use all the resources you have, but you really need plasma propulsion. For getting to the Mars, you also need the energy for that. And that's what the fusion compact system that's why we work on that.
Okay, so the plasma rocket is not the same thing as a plasma fusion rocket, because the fusion is just a whole other source of energy.
Yeah, so the plasma rocket, the energy can come from just some solar panels, because for example for the moon we have the sun sitting there, so we can get use the solar panels
But that can't
to get the power.
But that can't be the level of compared to plasma fusion. Getting through solar panels cannot give you the same level of energy.
It's enough. You don't need that much of a power to do that, like 500 kilowatt.
So I just want to settle my understanding on this.
Yes.
When you have a plasma, you have high moving particles. You can send them out the back and you recoil.
Yeah.
And the acceleration is slow, but it's steady and it accumulates.
Yes.
Okay. So if you have solar panels, the solar panel is not itself a propulsion mechanism, but it's a source of energy.
Yes.
And you can channel that energy back into your plasma and keep the plasma going as long as we're close enough to the sun.
Exactly.
Okay. Now you're really far from the sun. You still need an energy source. And what would that energy source be if you can't use solar panels anymore because the sun is too dim? Would that be the fusion?
Source, yes. It's fusion. It has to be non-chemical.
Yes, and non-chemical. So
it has to be
your
non-chemical.
fusion source of energy would still be heating the plasma.
The fusion.
I had not appreciated that. It's still a plasma rocket.
Exactly. It's still a plasma rocket because your magnets, first of all, you can use several, but you still have to power your rocket. And the source of power, it could be solar panel, or it could be the non-chemical fusion energy.
Plus, there's plenty of hydrogen gas in the universe.
Yes,
so you can just scoop it up, put it in.
When it's going through space, is the plasma sort of morphing and changing, and do you have to account for that? I mean, because it can survive. My understanding is it can survive plasma in various states, right? I would imagine you have not been able to document every state that it can survive in, right? It's an ever-evolving science.
So it's just that basically you need, the fuel here is like hydrogen, helium.
Right.
Yes, you have the fuel. You can actually use the local resources in a space for the fuel. So
and
that's
NASA
one
calls
of
it ISRU,
yeah.
In situ resource utilization.
Yes.
Which is a terrible acronym.
Yeah.
But ISRU, that's the big thing.
Yes.
Because then you don't have to haul everything with you.
Exactly. So that you want to be, that's why we call it efficient. Basically, it's fuel flexibility. And it doesn't have to be helium. It could be hydrogen, any kind.
So there's it can't exist on its own. It needs some other source of energy.
But what can't exist?
The plasma.
No, the plasma. Then you kind of you create it, you ionize it, you create the plasma. Yes. So that's the specific. You have to read the paper and the patent. You see how the plasma is created from this fuel. Local fuel, and then you get the plasma. But as soon as you create the plasma, you get rid of it from the back of your rocket by the process of magnetic reconnection.
And you've got to lose some of your mass every time you go and going to go anywhere.
But that's what I was saying earlier. Magnetic reconnection is it's plasmoids get created. They're not very unstable, but then become over time unstable and decay. Magnetic reconnection there's this constant instability and how you control that, and are you still working on being able to control that?
So for rockets, for plasma propulsion, we are not confining anything. So we don't care about stability, because in a fusion device, you confine plasma, you don't want it to go unstable. For a rocket, you just make the plasma, you use the magnetic field.
And then you just pollute space.
Yes.
Exactly.
I get it.
You get rid of it, and then you make new plasma and get rid of it, and then the rocket just gradually goes. As I said, 99% of our observable universe is plasma. It's basically some charged particles you have in space that you always have low density plasma everywhere in space.
See, she was good. She said the observable universe. Because we don't see the dark matter.
Yeah.
We don't know what the hell that is, but it's not plasma.
Yeah.
So she got that.
Yeah. Yes.
got
Yeah. So
this.
you could say that is.
Why aren't you altering with this plasma coming out of the back of a rocket?
Yeah.
Aren't you altering space in a way by putting these particles into space?
If space is 99% plasma to begin with,
We are floating in plasma in the universe anyway, so you kind of make some little plasma and get rid of it. Go somewhere.
Universe won't mind.
Yeah, universe won't mind. Yes.
How soon are we from having plasma energy generating centers in every city?
We are close, actually. Can
you give us a number?
5, but
5 years?
I would say 5 to 10 years. But that's a scientific network, again, I said.
Okay.
If you want to put it on the
engineers are good.
electricity.
I'm not worried about the engineers. They come through when you need them.
Right.
Okay, that's first. Second, when will we have rockets with humans in them that will use plasma propulsion? And will the first trip to Mars use it?
The first trip, I don't know, because it's possible that if all the resources are put there, you could get there once with chemical propulsion. But again, to have a sustainable kind of travel, so you need plasma propulsion. Actually, maybe we look at more closer places to go. And I think moon could be, as I said, it could be just plasma propulsion. One of the way to actually create fusion energy, it's something is called aneutronic, means that you you use deuterium, helium, to create energy, and you don't produce neutrons. So
that's just the PP chain in the center of the sun. There's no loose neutrons coming out of that.
Yes, exactly.
So that's a fun reaction in the sun. It's called the PP chain, proton-proton chain.
Exactly.
And it uses deuterium and tritium. No, I don't remember tritium, but we have helium-3 is in there.
Exactly. Helium-3, deuterium. So you have also fuel for also fusion. So there are things there. And you want to make some steps for the next generation, non-chemical propulsion. You first make some good progress, and then gradually going further, you use fusion energy.
How does AI factor into any of your work, or will it, in terms of the advancements you're trying to make?
Definitely. Computers. First of all, most of the progress we made in plasma physics and fusion have always been, together. Experiments and advanced computation work together to make discoveries, and also any kind of achievement, it has to be together.
Give me some words for the future.
Progress and discovery doesn't happen overnight. It's the continuous work of scientists, long-term investments, to you put all the energy you have, collaboration, all of that, and cross-pollination of various types of, group working on various types of plasma or types of devices, fusion experiments. Progress happened like that. So it's not. So it's also new physics. We learn every day in every regime of plasmas. We learn new things, and we apply it. Like this, rocket thruster. We apply it for other applications. What we learn in fusion, we also apply it for other applications. And so it's a continuous work.
So Fatima, typically at the end of our our sessions, I offer the viewer a cosmic perspective on the topic
Yes.
of the day. But you so beautifully summarized the plight of the scientist, the engineer, society, funding sources. That's any and all that I would have said in my cosmic perspective.
Thank you.
So thanks for making my job just a little easier. We got a good show today. Oh my gosh.
What's on
with
tap?
The future of the space industry. We combed the land
Yes.
to find somebody who's been in and out, and in that whole field.
Oh, right on.
And we got a man right here. Jeff, did I pronounce your last name correctly? Thornburg.
That's correct.
There you go,
Yeah.
Jeff Thornburg. So you are currently CEO of Portal Space Systems.
Yes, sir.
I love that.
That's very cool.
Aerospace engineer.
Nice.
We need more of those.
Yeah.
And you have a background with the Air Force that might have been the Space Force if it had been now. NASA Aerojet.
Yes.
Love Aerojet.
Wow.
SpaceX and more. So you've been around.
I've been around.
But it sounds like you can't hold down a job.
I grew up like I think you and others did and aspired for this science fiction world that we all would like to see. And I would go work at these places and be like, not moving fast enough, not moving fast enough, not moving fast enough.
Very cool.
And so,
And then you decided to take it in your own hands.
yes, sir.
Tell me what is Portal Space Systems and why that's different from what you've seen before.
Portal is building the most rapidly maneuverable spacecraft that's ever been built. And that's important because we're doing it with a lot of payload flexibility. So what that means is we can accomplish a lot of missions for defense and commercial customers. We can do it with speed. The problem with movement on space is you can't get anywhere very fast right now, especially with satellites and defense systems. So I got frustrated and I said, this is a solvable engineering problem. Why aren't we doing more about it? Okay, if no one's going to do anything about it, I'm going to go do something about it.
And
that's how
engineers
it
just love problems.
They do. They do. And they love developing new types of spacecraft.
So when you say get somewhere faster, you want to get to 9 months is not fast enough for you to get to Mars.
No, I want to do, no, absolutely not.
Okay.
Wow, look at that.
So I think my vision, my long-term vision is nuclear thermal propulsion, I think is a key thing in my lifetime.
As would be, that's anyone.
Sure.
So you're talking about how nimble can you be in the space, in the 3D space environment?
Yeah, so our current spacecraft platform can move from mid-Earth orbit to low Earth orbit in less than 3 hours. It can move from mid-Earth orbit to GEO in less than a day. It can go from low Earth orbit to geostationary orbit in a day. So those types of time.
That's not fast enough for you?
That is fast enough for me.
Good.
It's just not possible with frequency now, unless you're using a rocket to do it. It's not a routine thing.
So you're like, I'm going to turn commercial space into trucking. Once we had containers coming in and container shipping, like the trucking industry boomed because somebody had to figure out a way to get these containers where they had to go, and quickly. And so like you're doing that, which is
our customers don't care about how cool the tech is.
Right.
They just want
speed.
They want it now. If there's something going on in the world they need to be looking after, they want it do it now. If they've got a spacecraft in trouble, they want to see it now. They don't want to agonize over, well, if I move it, maybe I'll never get to move this spacecraft again because it doesn't have enough.
I didn't even know that was a problem until you just said it right now. And let me not even think of it as a problem. Let me think of it as an unrealized need that you are fulfilling. Very nice.
That's right.
So we'll get back to that, but tell me, because you had your whole life is in this, and we're probably about the same age, so I'm feeling your enthusiasm and your disappointments. What are some things that you have worked on that you could tell us about?
One of the most exciting projects I got was when I was a young engineer with the Air Force Research Lab, and I got to develop a brand new type of rocket engine called a full flow stage combustion engine. That's a fancy name for saying the highest performing rocket engine ever made.
And just to be clear, Air Force Research Lab, that's not just another lab on the street corner. That's an FFRDC, if I remember correctly, or not?
It's a government lab.
Okay.
There are contractors like aerospace that support in an FFRDC way.
What does that mean, please?
Federally funded research and development operation, where it's a way for the government to get a piece of a pie that's being baked that corporations wouldn't otherwise do because it's a little risky. It's a little kind of off the thing, but
no business case. Got to work on that rocket engine program, and it formed a kernel of several kernels of technology that seeded the propulsion industry for years to come. So I got to work on that program between 1999 and 2004. And then that seeded engine programs like J2X that were part of the Ares rocket program. It seeded things like what Stoke is doing with their full flow engine. It seeded what I did with Raptor later on at SpaceX, because I developed and architected the Raptor engine system for Starship. So
when SpaceX rose up out of the din of rocket corporations, were you cherry picked? Did they cherry pick you from your previous location?
I don't know that I ever got the full story, but this is a true story, is that Elon called me at home in Huntsville and said, I got a project I think you might be interested in.
So that counts as being cherry picked?
Shortly after I left NASA in Huntsville and went to SpaceX.
It's Huntsville, Alabama.
Huntsville, Alabama.
And of course, we just learned that the headquarters for the Space Force is moving from Colorado Springs to Huntsville, Alabama.
Let me ask you both this then before I know, because you brought up these FFRDC.
Yeah.
Is that still necessary now that there's so much commercial activity in space travel? And is it still necessary for the government to seed money into things so that we can then go forward in discovery?
I love your question, because what I've been watching happening in the quote new space industry is venture capital and businesses chase things that add value or add to the stock price or add to profit. The government and the FFRDCs focus on necessary technology that there's no business case for. So
no business case at the time they're funding it.
Okay.
Who knows what'll happen after?
So I feel that FFRDC should definitely be seeding new technologies like the ones we're developing at Portal for this rapid movement, because no one else is going to do it. So NASA and the Air Force have done a great job over the years of developing technology that then they later put next to the Ark of the Covenant in the warehouse at the end of Raiders of the Lost Ark. And I've been fortunate enough on a few different occasions to go back into the warehouse and pull some of these things that the government has developed. But when I was in the Air Force specifically, one of the biggest issues is that nobody has that foresight to know all of the ways that technology will be applied.
Right.
And that's why
nobody has that.
Right. That's why it's so important to keep the government involved in pushing that boundary. And I think that's where the government should be spending their money. Unfortunately, those government budgets are shrinking because I think some people think, well, private industry is just going to do it, so why do we have to fund it anymore? But what they don't understand is VCs and private industry are chasing value creation and stock price and profit, and that may not be in the same wheelhouse as the technologies we need to actually get humans to Mars, to get humans to the moon, and to explore the solar system.
So tell me about Aerojet. What'd you do there?
I worked as an engineering manager and director on liquid rocket engine technology development, did a lot of turbo pump development for liquid rocket engines while I was there.
I mean, we've had liquid fuel forever. I mean, since Goddard, right? So what new thing was necessary?
Getting weight out of the system.
Oh, every ounce matters.
Every ounce matters. And combining components, bringing in technologies like additive manufacturing to reduce part count.
Wow.
And figure out how to qualify systems to do that.
If you reduce part count,
yes,
that reduces the error, the points of failure.
Correct.
That could take place.
Reliability goes up as part count goes down.
Because I remember when the shuttle first came out, okay?
Yeah.
And there was this headline that sounded like it was bragging, and I said, that's not a brag. It said, the space shuttle, it's the most complex rocket ever to be launched. And it's like, you don't want that.
Yeah, right.
But am I right? I mean, you're the
correct.
engineer.
Yes.
It's like, don't tell me that.
Well, in fact, they couldn't reuse it the way they wanted to because of that fact. You know, shuttles were going to launch 25 times.
Yes, every couple of weeks.
Every couple of weeks. And then they're like, oh, these engines aren't as easy to refurbish as we thought. We've actually have to rebuild them after every flight. Oh, we got wiring issues that we hadn't accounted for. Oh, we've got tiles.
Tiles, right, that'll fall off.
Right.
So when the shuttle was retired, we didn't have a way to get to space.
Yes.
And so I guess we used with Russia. I mean, they were our friends back then. Who knows what they are today? But they had the Soyuz capsule. Does the Soyuz capsule have like 10 parts to it or something? It's kind of a blunt instrument that works every single time. Tell me about the Soyuz.
Well, the Russian...
And you testified about that. So catch me up on that.
I mean, the Russian development of rocket technology is interesting because you have to go all the way back to the end of World War II, We cherry-picked rocket scientists. The U.S. grabbed their lot, including von Braun.
Werner von Braun, yeah.
Russians grabbed their lot. And what happened was the Russian lot of German rocket scientists really ended up focusing on reliability and part count and manufacturability. Von Braun and his team, and what later became the bulk of NASA, focused on performance and perfection. And so there was two completely different thought processes between Russian rocketry and American rocketry at that point that can trace themselves all the way back to the end of the Cold War.
And that persisted. And so to this day, the Soyuz, isn't it the most reliable?
It is, and it has heritage dating all the way back to the 50s because they've never changed it. And their technology, there was so much elegance in their manufacturing that we ended up buying a lot of their engines at the end of the Cold War because we didn't want the Russian rocket scientists going to Iran and North Korea and other places.
That was part of our relationship with the space station to bring them on, give them something to do. In the day, everything that NASA launched said NASA on it, even if it was built by Boeing or Lockheed Martin or whoever else. But private enterprise is now putting things on the shelf that NASA then selects off the shelf, and that all has the name of the companies on it.
Yes.
So this is a shift. Could you take us through that shift?
Sure.
From the old days into what's actually happening now?
Yeah. So about the time, the early 2000s is when Blue Origin and SpaceX were incorporated. And then over the next 10 years, they started to develop capabilities to launch things that were interesting to NASA. When I was at SpaceX, and we were developing Falcon 9, they didn't believe that we could do those things at those price points. So they kind of patted us on the head and said, that's cute, let us know when it works. And then it did work. And then that's when the real interest came forward, because now for $60 million a launch, you could do a lot of cool things that you couldn't do with the Space Shuttle program. And then the race was on.
Space Shuttle was $1 billion a launch or something?
Something
it
like
turned
that.
out huge.
Holy
yeah.
moly.
Yeah, part of it was because there weren't as many launches in a year to amortize the cost of the marching army to keep all that going. And with more launches, then the less per launch the effective cost is. But if you bring the cost down to that, that's another ball game.
It's a whole other ball game. And that's what got us excited about the shuttle retiring, because the race was on to get Dragon on a Falcon 9 as fast as possible and get astronauts to the station and get American astronauts again to orbit. And we put all the NASA logos and everything, and they were a great partner and all that. But, it was weird because people would come up to us and say, does NASA exist anymore? Because SpaceX seems to be launching everything.
So let's get the animal straight here. So the Dragon is the capsule.
Correct.
The Falcon 9 or the Falcon Heavy. The Falcon is the rocket, the launch system.
First and second stages
of the system. Good. Just get the animal. If you were,
yes.
Were you up with the animals there?
Yeah. We didn't we go to SpaceX and I think you said it's the number of.
Well, it looked like it. Is it true? The Falcon 9 has 9 engines on the bottom.
That's correct.
Okay, because we visited the headquarters and
nice.
Yeah, it was one. We had StarTalk goes to SpaceX.
Yes,
I think it's online.
Yes,
and we were just chilling and looking at the rocket, and yes, the one that it's the first stage that comes back.
Correct.
Right, and you see it with the tripod.
Yep,
a big one mounted outside.
And we had to put that engine in the center to help facilitate the landing burn.
Right. Let me ask you that: if you're going to bring the stage back, that means you are using weight for fuel to guide the thing back for a soft landing. But I want that weight for my payload. So where do you, as an engineer, where do those two lines cross?
So the elegance in the engineering is that Falcon 9, basically, we actually pushed that vehicle to its absolute limit before anybody ever saw it do its thing. And we did that because we didn't want any excess fuel on that vehicle when it landed back. So then what we did, the company did, the business people did, is they said, look, we're going to sell you an expendable stage or a reusable stage. And if you do the reusable, you'll save some money.
Oh, so then the buyer makes that decision.
That's right. Then the market.
That's brilliant.
The market chooses.
Brilliant.
What did the market choose? They chose the reusable version because it made the most financial sense.
Wow.
But so there's two things. There's a business
model.
I'm
glad to hear that. That puts a lot in context for me.
Right. as an engineer, I have to make that system as efficient as possible, meaning there should be no unused fuel when it lands, and then let the buyer and the market choose that configuration because it makes the most financial sense, and then everybody wins.
Occasionally, you need the payload, which, if memory serves, they needed that extra weight for the Europa Clipper mission. I think the first stage did not return smoothly.
I think
that got dropped into the ocean.
Right.
They needed that.
You got to have all the Delta V available to go to Europa.
Okay.
So,
Yeah, Europa is the Jupiter's moon.
Right.
Yeah, the Europa Clipper will loop around,
Yes.
make radar measurements beneath
and
the
they'll
ice.
sell that. But I think the business case people should understand is if you buy an expendable version, now that hardware can never be used again. And there's value associated with that hardware. So you're going to pay to basically use it all in one shot. And so that's another way to drive market value. That's a good business case as well.
So at the risk of asking the obvious, all these places you've worked, presumably there's a lot of wisdom you have gleaned from that you bring to your current job. Is that a fair statement?
I've seen a lot. Yes, I think that's a fair statement. That's
Yeah.
definitely true. But I got to work with these graybeards at NASA and the Air Force, older folks that had seen a lot more things than I had in my career.
Give us a minute. We don't always have engineers on the show. It's mostly scientists. And for what it's worth, anytime people say to me, oh, you guys are doing great things in space, I say, look, we know what we want to do, but we don't know how to build the stuff. There are engineers who you never come interview who enabled the James Webb Space Telescope, who enabled the Hubble telescope. And so I just want to, on record, give a shout out to nameless engineers who
Are
make the
responsible
scientists
for the success of everything.
of everything and make the scientists look good, but you only see the scientists get interviewed because they're talking about the results of the experiment.
Right.
And whereas the engineer is not in that loop. So
I think that's awesome that you're doing that. And two, that's the best part of my job is like, I know engineers that got degrees that never really became engineers because they never got to actually experience an idea that you actually have to go build and it needs to work. And then I work with people every day, some of which that don't understand that engineering is sometimes an art form because you don't know all the things. You have to design around the uncertainty. Like if you came to me with a new spacecraft system, I'd say, yeah, that's theoretically possible. Now let's go see what we can actually build and how accurate I could build it.
So I just want to highlight for our audience, which is primarily a science-leaning audience rather than engineering-leaning, tell me the value of failure. Let's just start there.
I'll answer that with a quick story, which is a lot of legacy government and NASA programs have this failure is not an option moniker to them. And what that means is to have infinitely low risk requires infinitely high cost. And so that's not how a lot of commercial startups and businesses have formed in the last decade or so, because instead there's a different approach in engineering where we want to actually break it because we want to see where the design fails and what we don't know yet and what we need to fix. And I think a lot of the legacy NASA programs have suffered at times because they've had to try to get everything right on the first go. And that's a pretty tall order. And that's why these aerospace programs have taken so much longer than anybody ever wanted from a schedule-wise or from a cost standpoint. So I think
Elon in the early days was very visible with his rocket failures.
yes,
And he made a very important point at every turn. We're going to learn something from this. Although it sounded a little too euphemistic at times, where the rocket blows up and it's, no, that was not a failure. That was an experiment rich in data.
it's true to a certain extent, but not all failures are planned, and most
Right.
of them aren't.
Mhm.
And but the value is if your company or organizational culture accepts failure, then you will actually get to the end product much faster.
There it is right there. That's it.
As Neil knows as well, look at the history of the Mercury, Gemini, Apollo program. We blew up a ton of stuff.
Yeah.
Those young men and women were in their 20s. They looked like SpaceX looked a few years ago.
Wow.
And so NASA used to operate exactly in that mold, but somewhere along the way, politics took over and it got different for them. So I think NASA should focus on the programs that aren't viable as a business, that are pushing technology forward, because I think that's what they do really well at. I don't think they do well in big rocket programs. I mean, just
Well, this is my reply. I'm asked it often, as you can imagine. We said it earlier. With private enterprise coming in, why do we need NASA? Because there are things that private enterprise would never engage on the frontier, where there's either risk that they would not take or return on investment that does
That they
not
will
exist.
not make.
Right, exactly.
And I don't think nation states should rely on CEOs to be their only hope in achieving certain national goals.
So you want people to be more comfortable with failure because that's how you proceed. Not failure from blunder, but failure from something you had not seen coming. It's a different kind of failure, right?
I think people think engineers just know,
Yeah.
and therefore when we fail, oh, we're stupid or we're a bad engineer. And they don't understand the art of engineering is designing a system around unknowns, and that we don't always know the first time it's going to be successful. So I think
Which would include the unknown unknowns.
correct.
Mm-hmm.
I think that's the unlock for people to know failure is a good thing, because you've now given engineers a gift, because now they have all of the information. So that's why failure is so important to engineering, because now you've pushed the design all the way up to the line. You don't have to guess about it anymore. So now you've gone from that initial phase of engineering around the margins you don't know, which normally means it's heavier or carries more fuel or less efficient in some way because you're just trying to get it to work. And when you fail it, now you can totally isolate that to what it needs to be. And that's why things like the Falcon 9 first stage land the way they do, because we failed so many of those, as the gag reel has shown over the years.
Yeah, back when you were at SpaceX.
Uh-huh.
Yeah, yeah. This comes up, and I want to hear it. I've spoken of it as a scientist, but I want to hear an engineer speak of this. Let's say there's some disaster, NASA disaster, okay? Always, somebody digs up an engineer's memo that said you shouldn't launch because this might fail. And then others say, why didn't you pay attention to that? And nobody looks to all the successful launches to dig up the very same letters that say you shouldn't launch because that's going to fail, and it doesn't fail. So how do you square how NASA or any company should respond to the claims that you didn't heed advice, when presumably, I'm thinking, there are memos like that every single launch?
So there's a failure in leadership there that I personally believe in, that I operate differently in my organizations over the years and my company now. You're always going to have somebody say, I'm worried about this before you launch or before you field a spacecraft on orbit. And so what I do is we have what's called active risk management, which is a NASA term. But we look at all those risks before we fly. At every organization, there needs to be a person that signs off on the final risk posture for whatever mission you're flying. And that person, it's okay for them to take risk, but they need to document why they're taking that risk and why it's acceptable. So when I build flight hardware, we do a final risk review before it flies. We look at all of the key risks. And if people feel really strongly that they're worried about something, then I say, I'm taking that risk away from you. You don't have to stress about that anymore. I'm going to say it's okay, and I'm going to justify it because of this.
Okay, so now something goes bad. Now the press comes and they see that memo. And
Right.
They say, why didn't you heed the advice of that memo?
And I had already addressed that in the documentation that said, I thought this was an acceptable risk because of X, Y, and Z. And I know I have to stand by that, whether it fails or not.
Okay.
I make it a point to have acceptable risk documentation. So if the worst happens, I can at least explain myself on why I thought that was okay.
Gotcha.
And then I'm also fine saying I was wrong. In space, there's never a guarantee. That's the thing.
No such thing as safe in space.
There's no such thing.
It's just the risk that you accept.
I think companies get into trouble when management takes that authority away from engineering and says, we don't care what you guys think, we're doing this
Oh,
anyway.
that's when you got a problem.
That's when you got a problem. And so when you're talking about, door hatches blowing off or submarines failing when they shouldn't have been designed the way they were or whatever, that's a failure in leadership.
Gotcha.
And so I think you're still going to have failures. And I'm just saying, let's avoid the failure
That's
in leadership
interesting.
piece of that.
Not enough attention is given to where the leadership matters versus the engineering declarations of what the risk factors are.
That's right.
Yeah, yeah.
Because people just want to get to the end.
Okay,
they
so
get
how
large
about,
fever.
just since we're here, the Hubble telescope, the mirror has a perfect shape. The secondary mirror has a perfect shape, but they don't play in the sandbox together, and they were not tested together. So is that leadership?
That's a failure in system engineering, in my opinion, because you didn't have an adequate test program.
How big was system engineering as a thing at the time? We're talking about
We're
the
talking
late
about
80s.
NASA. This is system engineering haven.
That's what it is. You're right.
So, of
But I
all
don't think
the
I don't think system engineering was taught in schools as a branch of engineering until later than it should have.
Well,
am I right there?
I mean, I've seen evidence in the shuttle program that they had very robust system engineering back in that time frame.
okay,
So,
in the 80s.
you know,
then,
maybe
the
NASA
90s,
didn't
yeah.
equivalently apply it all over the different centers and
Gotcha.
programs, but there is no better place for systems engineering execution than NASA.
So that's a blunder. Somebody.
That's a failure of imagination to be like, should we test these systems before they fly? Maybe.
Wow.
Let's go back to the Mars Climate Orbiter, where it never got into orbit because the scientists were using metric, and you engineers were still on imperial units of force.
We've carried mixed units in the United States for way
Oh,
too
be
long.
blaming the country.
A lot of the engineering tools for spacecraft and launch vehicles were all written in imperial units. And so they've been very slow, the community at large, to change those tools to a metric standard.
Okay.
And so engineers get lazy because they want to stay in the units they're comfortable with.
So we've seen in recent months a move to cut costs at NASA. Cut costs in many ways, including the science budget, I think got the biggest cut. And there's some attrition, people leaving and not being replaced, early retirement. And so it seems like we're losing some legacy wisdom with that shift. Could you reflect on what you think might be the future consequences of this?
Absolutely. What comes to my mind, there's two things that I actually worry about now, which is we're watching our scientists walk over to other countries because there's no funding for them here.
I know I have two colleagues, not in astrophysics, but in other physical sciences. They said they got a phone call from France.
Yeah. So you've got the scientists vacating, and then you've got NASA engineers and folks that will not be doing the fundamental research. We've been robbing R&D from the United States for, my career has spanned 30 years at this point. I can't talk to all the things that happened before me, but I can talk to all the things that happened in 30 years in my experience. And it was bad when I started my career. It's even worse now 30 years later. I think current events are going to have ramifications for America as a leader in science and technology for decades to come because of what's happening now. Because you don't know which experiments are going to work.
Right.
You have to fund a lot of different science and technology areas, hoping that 1 out of 10 or 15 are going to be winners.
Speaking as an academic, if I come up with a great idea and I publish it, and then all my colleagues see it, they can judge it, see if there's a flaw, or use it as a stepstone to reach a next goal. That's the openness that is fundamental to the progress of science. You're in a competitive industry. If you make some discovery, would you be resistant to patent it because then other people would see it? How does intellectual property work in your business?
There is a strong desire to hide things that are unique because it becomes intellectual property and IP of the business that can actually add to its value. One of the things as a CEO of a space startup that I think about a lot is integrity. And so to your kind of what you're scratching out a little bit is if there was something so great that could benefit humanity, I learned a lot from Paul Allen when I worked for him because one of the things I took
Microsoft Paul
Allen. And one of the things I took away from Paul was technology for the benefit of humanity. So that's one of our kind of cultural touchstones at Portal Space Systems. So if we had something so great and so beneficial to humanity, I wouldn't want to hide that. But that's just my take on integrity. But we don't have enough integrity in the business right now, is a personal observation. Because the push to make money, the push to grow a business and satisfy investors sometimes compromises people's value systems in ways that aren't great.
So how could that, because it seems to me like what you're doing is either comes down to this works or it doesn't. So I'm sure there are people who feel like, well, what do I need integrity for? Because it either works or it doesn't. So what difference does it make? Where exactly does a lack of integrity hurt the business and then subsequently
I think lying about the progress of your product. That's where
to
I
keep the
see
money
it.
coming.
That's where I see it the most.
I see.
Businesses are trying to drive for that next fundraise,
Gotcha.
that next investor,
Okay.
and they lie their asses off to get to the next step.
The billionaire boys space race. I mean, they're billionaires and they had the cash. How does that work compared with someone who has a brilliant idea and just gets VC money to come in and help them?
Yeah, well, with Elon, he had that money from PayPal to start Tesla and SpaceX. So he had a $100 million head start that most people don't have.
Yeah, VCs will come up with $100 million.
You have to work at it. It doesn't happen that fast.
Okay.
Normally you still end up going through a process where you're going to raise a pre-seed round of a few million and then a seed of maybe 10 or 20 million, and then
Plus,
blah,
you
blah,
owe
blah.
the VC at the end, where if Elon is spending his own money, he just owes
You're
himself.
diluting your business every time you raise money.
Yes.
And Elon didn't have to do that because it was his own
It's
money.
his own money.
To begin with.
So let me ask you, because I'm just fascinated by this whole thing right now. How does a VC know anything about thermonuclear propulsion? Like, I need $30 million.
This is where he's got to be a salesman.
When we started the company 4 years ago, we decided to pursue solar thermal propulsion because it was a stepping stone to get to nuclear propulsion later. But nobody knew what that was or how it could translate into getting you faster movement on orbit. So you're right. The CEO has to be a salesman first, and then you have to start proving that you can build this hardware. And then you start building hardware, you start doing testing, you start showing people.
Plus, you're going to assemble a board of some kind who's looking over your shoulder.
Yeah, but the investors typically don't know anything about the technology, to your question. And they hire people.
That's not unique to space, right?
No.
Almost all the high-tech frontier companies, VCs just like the idea.
So one of the things we did at Portal was we started working with the Space Force and the Air Force on small business innovative research contracts so that we could show people that knew things about space, that knew the technology, that investors could then get confidence on, that we were on the right track of things. So there's just a lot of steps you got to take to try to convince people something's real. And I wanted to do that with data as much as salesmanship.
Could you give us a kind of overview on the history of propulsion and how the ideas have landed, what's working, what has underperformed relative to predictions, what has overperformed? What we do know is that we don't really have flying cars. We have these flying drones, okay? They want to call them flying taxis, but they're helicopter drones, all right? So in the old days, there was just simple Goddard liquid propulsion that you can throttle, I guess. It's chemical energy.
Yes,
We're still using chemical energy.
we are.
So what's up with that?
Well, to get out of Earth's gravity well, you want a lot of thrust, and liquid rocket engines are still the best way to get off the ground and into orbit. Where technology has now started to evolve is once you're in orbit, now what do you do? I would argue that liquid rocket engines aren't the best way to get you around once you're on orbit. Now, we're still using that to take upper stages, third stages, second stages to take you to higher orbits and stuff, but that's not the most efficient way to go. And so they started to see this with...
So there are these regimes.
Yes.
There's acceleration regime, delta V regimes
Yep.
that don't call for the same solutions.
Correct. There's more solutions available than what we've typically used before.
Okay.
So the electric propulsion came on the scene a while back.
And tell me how that works.
So typically you're talking about a Hall thruster type system. So you're creating ions that you're accelerating out the back of an electric motor or engine.
Why isn't that an ion engine?
It's an ion engine.
I thought it was something different, but it's not.
Electric propulsion ion engines are in the same family. They're very efficient, but they don't have a lot of thrust.
Right.
So because you're not creating the acceleration, because you don't have a lot of thrust, you don't get anywhere very fast. So satellites said, okay, that's cool. If it takes us weeks or months to get to an orbit where we're selling electrons for broadband internet or TV or whatever, that's fine. But then our adversaries started developing spacecraft that could move a lot faster with higher thrust. And then they started doing things on orbit that threatened some of our critical infrastructure. And now we have no way to kind of maneuver around that.
So there's strategic value
Yes.
to this.
Maneuverability is a key ingredient of warfare on land, sea,
And
air,
space now.
and now space.
You think? So chemical rockets, we are removing energy that was built into the molecules that are in the fuel tank. That energy gets released. You expel mass out one end. The rocket recoils by going the opposite direction. Newton's laws.
Yep. Accelerate those particles in the thrust chamber as
With
fast
very
as possible.
high mass, high speed coming out the back. Once you are in place, you now kick out ions, which have very low mass, but high efficiency. And so it'll move you if you're patient.
Yes.
And so these are two different needs,
Yes.
clearly. Okay.
And now there's a new need, which is we don't have that patience any longer.
Right.
Got it.
Now, what are I'll say our adversaries? What are they using for maneuverability?
Well, if you
on
look
orbit?
if you look at what China's done, as they've grown the amount of mass they can throw with their long march launch vehicles, they're just making bigger and bigger spacecraft with bigger and bigger tanks and bigger and bigger thrusters.
So they're brute forcing it.
yes, sir.
Okay,
That's correct.
That's what they're doing.
And we like to be more elegant.
Yeah.
Remember my story about the Russian rocket
Right,
versus
exactly.
American?
We-
We always want to think about everything.
Right.
As my wife often tells me, I'm in my head too much. That's very much an American.
But you know what?
That could
I
happen.
kind of feel like precision and elegance wins out in the long term if you can get past the short term.
in commercially, yes.
Yeah.
Because you need that elegance to hit a price point that's going to make you both commercially viable and viable for the defense industry
Right.
as well.
Yeah. And unlike America, they spend as much money as they want on anything that they want.
Well, and China's completely aligned in their military-industrial complex.
Right.
Yeah.
I mean, there's only one
There's one
chain of
chain of
command,
command. Yeah.
one person that makes those
Right.
decisions.
Exactly.
Is there anything you could testify in Congress today that's reminiscent of what you testified back in 2015
That would let them
about
know
our
that-
needs,
and to
the
let them know.
transition of our needs?
When I testified before Congress in 2015, it was about, why are we sending all this money to Russia and buying their engines when we've got engineers we need to train in the United States and we have commercial companies that can do the job? And that was my argument. And I said, hey, Falcon 9, Falcon Heavy, Starship, Raptor are coming. It's going to be a thing. Fortunately, I was right on all of that. What I would say today to different committees before Congress is, our adversaries are coming for us, and we are cutting R&D spending, we're cutting engineering, we're cutting science, we're cutting all of the things we need to be competitive.
We're also spooking immigrants
Yes.
who could have expertise, as they've always had.
Yes.
I mean, when I was in graduate school, half of my fellow graduate students were foreign nationals. Half of them.
And
now they're all spooked because they don't know what's going to happen.
yeah, and China's made no bones about they want to be the preeminent superpower in the world. So I don't know why we kind of have our heads in the sand about this. If I was testifying before Congress to your question, I would be hitting those points really hard, because we need to be accelerating capabilities that are going to preserve. I want to preserve low Earth orbit, mid Earth orbit, LEO, cislunar around the moon for commercial opportunities in the future. And so my thesis is, if I don't do my part to protect and defend it with the Department of Defense, there's not going to be a spot to make money commercially in the future. And that's how it's been. So we started sailing wooden ships. The pirates were there. It's going to be no different on orbit. So what are we going to do about it?
Yeah. And so let me describe what I think is going on in space, and you either say I've got it right or modify it as necessary. When people hear Space Force, they say, oh, there's going to be weapons and bombs in space. And it's not really what's happening there. What's happening there is our assets that enable what we think of as modern life and civilization are fundamentally pivoted on what we have orbiting this Earth, with the satellites, the GPS, especially our other communication satellites. And so if you have a military, it's not, oh, defend this border, take this hill. No, it's defend our assets. And our assets are bare-assed in space. And an adversary who wanted to take us out, blind us, they would go to our communication satellites and take us out.
Just like Independence Day.
It was Independence Day. You remembered that.
That's right.
The aliens came and took out all of our satellites.
Leave the World Behind on Netflix.
Leave
Oh,
the
that's
World
another
Behind.
one.
That's a great one.
Leave the World Behind.
Yes.
It was a tech warfare. It's
Yes.
not. Would you agree with how I've
I
characterized it?
loved how you characterized it because that's the same message that I try to send when I'm talking to, why should the average citizen care about this? They should care because when they go to the gas pump, it's not going to work because GPS does the timing for the gas pump. When they go to get cash from the ATM, it's not going to work because GPS does the timing for the ATM. We've selectively tied our financial systems to GPS, and we did that. We made a choice. We said, oh, this is cool. Let's do this. This is handy. China did not do that. They have other ways they do timing for their banking. And we made fundamental decisions with our space technology that have made us vulnerable, to your point, which is why people should care so much about this
And we have
problem.
battleships and Marines that could do 100 push-ups and launch silos. And any country that's smart is not going to attack us on those grounds.
Right.
It's going to find, you're just going to find a weakness. That's how any war unfolds.
Well, and guess what? All those assets up there right now, can they move when they're threatened? Can they defend themselves in any meaningful way? I would argue probably
No.
not.
And I also heard, and I haven't confirmed this, but I heard, and you would know, that some adversaries will have satellites that'll nestle up next to our satellites and just basically harass them, either with an electromagnetic field or something. And so we then have to move our satellite away from them to maintain operability, but that uses fuel that we otherwise need to station keep. And so that will reduce the lifespan of some of our satellites because of this. And no, did it fire a weapon at us? No.
No.
Did it destroy us? No. It's just,
It just cyberbullied us.
ooh, yeah.
This
Orbit
seems
bullied
like
us.
a very reasonable hypothesis to me.
So in your current capacity as CEO of, give me the full name again?
Portal Space Systems.
Portal Space Systems.
You'll have to ask me how about the name of the company at some point.
I'll ask it now. How'd you get Portal Space Systems?
I used to watch Rick and Morty with my daughter.
Excellent.
There it is.
And so half of the story is the portal gun from Rick and Morty, because that's what I used to watch with my daughter.
You know, Rick and Morty is just Back to the Future relationship all over again. It's Doc and Marty. So tell me what's the coolest thing you're working on in your company right now?
So Supernova, we kind of have a star theme with our products at the
Love it.
company. With Supernova, it's about that rapid movement. And it's Supernova because we're using concentrated solar energy, and we've innovated around a heat exchanger, so we don't have to combust any liquid propellants with our system. So like a nuclear,
But this is towards what end?
this is so I can carry twice as much fuel, and I have a thermal engine cycle where I'm not using combustion. So I can have fewer parts, more efficiency, higher thrust, and twice as much fuel because I'm not carrying an oxidizer, so I don't have to burn anything. And I really wanted to do nuclear thermal, but I can't buy a nuclear reactor at Lowe's. I joke about this all the time because the thermal engine is a lot like Mr. Fusion from the second Back to the Future movie, because we use ammonia as our propellant now, but we could use any
Mr. Fusion was
propellant.
in the first.
The thermal engine's a lot like Mr. Fusion because we can use ammonia, which is our baseline fuel, because it's very storable on orbit, and we have a multi-year life of our spacecraft. But if I want to start moving out to Mars and I want to use methane, in the future I want to use hydrogen, I want to use other things, I can use other fuels in a thermal engine system.
Oh.
So this
has versatility.
is versatility because I'm very much a live off the land kind of guy when it comes to space. If we're taking everything with us, we've failed as engineers.
That's so cool.
You know,
That's
could you
very
tell
cool.
NASA that that's what they should call it instead of in situ resource utilization?
If I'm going to Mars, I won't think of all the things I need to live, but I want a print machine that can print any tool I need
Right.
once I'm there.
Mm-hmm.
But anyway, so with Supernova, it's about propulsion, but it's about payload flexibility. So what that means is software definable power, which means you have a payload, you have a camera, you have a robot arm, you have whatever you want to do, whatever mission. It's like a Lego brick onto the front of the payload deck. Perform your mission. I'm selling, I'll get you there as fast as you need to be, and I'll give you a platform that's very versatile over multiple years.
Not to stupidly simplify it, but are you saying you have a warehouse and I have a need, and I say I want to put this object on Mars and do some things, and you say, yeah, to get two rockets from aisle A and 2 boosters from aisle B, and then we assemble what it is that will serve my needs?
Well, from a spacecraft standpoint, yes.
Okay.
So I am going to build you the spacecraft, and whatever you need on that spacecraft to perform a mission, whether that's a camera or a telescope or whatever, I can supply power and data to that.
That is engineering heaven right there.
That's wild.
Because that's one of the biggest problems with satellites right now is everything's bespoke. So you want to have a telecom satellite. Oh, I'm going to build the whole thing, including the telecom payload.
And that's
all
way
it does.
more expensive.
Yeah.
The one-off. It's a one-off.
And if your customers don't show up and want it, then your business fails.
Mm-hmm. Mm-hmm.
I can't predict everything the customer needs, so I didn't want to try. I just wanted to give them a spacecraft that could meet all their needs.
What's on our doorstep? What remains only in the dream states of engineers?
I think 2 things. If I was king of American engineering for a day, for space, I'd accelerate AI and machine learning and get more robots and AI out there doing the heavy lifting for us.
It's called Skynet.
We spend so much time and money trying to keep humans alive that it slows our pace of exploration
Everything.
on orbit.
It slows everything.
So let's get AI and ML out there on spacecraft, exploring the solar system and teaching us what we don't know yet.
ML, machine learning.
Yes, machine learning. So that then we can engineer the systems that keep people alive and get it right the first time. And we can get more exploration done faster because we're not spending all this money to keep people alive right now. Let's go learn what we need to learn to keep people alive. And then on the propulsion side, I think what we're learning in quantum physics, this is where I'm going to carefully delve into your universe for a hot second. I am not the expert in quantum physics, but I do read a lot because I'm super interested in what we're learning there. But I think there's elements of the quantum world that are going to unlock propulsion technologies that might look similar to a warp drive. But I think we need to unlock some more understanding of the quantum universe to do that. I think that's going to be the linchpin in giving us sci-fi geeks the warp drive we want.
A quantum FFRDC would be a cool thing.
That would be an awesome thing.
Right. It's just everything quantum.
And you could probably get that funded because there's a lot of defense applications for quantum as well.
Right,
God, yes.
right. We know when the warp drive gets invented. It's 2063 in Star Trek.
Right.
So those are your marching orders.
Okay.
Okay.
I think we can do that.
You got 40 years.
We're moving fast in quantum.
It's via the quantum.
Via the quantum.
Okay.
I think that's our best path right now.
All right. Because if you know, at least even in Back to the Future Part 2, they predicted that the Cubs would win the World Series.
And they did.
And they did.
But I think that with warp drive, it's not about this propulsive thing that we're all mentally geared to. It's how do we leverage quantum to manipulate the fabric of space-time?
So quantize gravity and things of that nature.
You have to you're going to have to figure out how to fold
We
space-time.
need a new understanding of the fabric of the space-time continuum.
Nice.
Manipulate that. It's not even about propulsion.
Propulsion, yeah.
Yeah, that's right.
Chuck, do you have any last questions for the man?
Yeah, I'm just interested, like, what would be the ultimate achievement in commercial space travel or the holy grail? What is it that everybody wants?
I'm going to tell you what I want, and then we'll go to him.
Go ahead.
I want to go suborbital to between any 2 points on Earth so that I'm no more than 45 minutes away from lunch in Tokyo and then fly back. So that would require rockets, not planes.
Yeah.
Because orbit is 90 minutes.
Right.
So if you're
So
suborbital,
you're
half of that, you just go the other way, whatever, you can go anywhere in the world. And I think about that every time I go to Washington. I go to Washington like for a lunch meeting and then come back and I'm home for dinner. What awaits us?
For me, my holy grail is that humans can go to any orbit between here and the moon or the moon. And it isn't a significant emotional event.
So
in my lifetime,
cislunar space becomes our backyard, not even worthy of comment.
Correct.
That's a worthy goal. I like that. Let me perhaps offer a cosmic perspective on this. I'm a scientist. I think sciencey things about the world. And at no time am I asking, how would one accomplish this? How would one build it? How would one pay for it? How much ingenuity does it require? Do I have to invent something that has never before existed just to solve the problem I have posed? I don't really have to think about that. And we have this community of engineers that walk among us who live for that. They live for it. You know what else they live for? Constraints on what it is they need to do. That was the most impressive feature of how engineers function. The last thing an engineer wants to hear is, here, go build this. There's no time frame, there's no money limit, and there's no constraints. They're going to be staring at their navel to not knowing what to do. But if I say, I got 3 months, I got $2 million, these are the specs, and this is the requirements, go. Their ingenuity derives from figuring stuff out within those constraints. That's how we make discoveries, not scientific discoveries about how stuff works around us that so many of us, myself included, take for granted. So, there is no future of civilization without happy engineers. Engineers that are given problems to solve. And maybe it's up to the rest of us to give them the kinds of problems we need solved. Energy, housing, climate. Scientists can't solve those problems. We can characterize them, but we need engineers to step in the ring. And this is an appeal, I suppose, to a few. Not everyone can be an engineer. We don't want that. Engineers don't even want that. But engineers as a demographic of society that'll lead us into the future, there is no civilization without them. And for me, that is a cosmic perspective. Jeff Thornburg, thanks for being on StarTalk. We got a full house today. First, Gary O'Reilly. Gary.
Hey, Neil. Hi.
How you doing, man?
I'm good. All good.
So we're going to do predictions about the future, which I think is the only way you can make a prediction.
Right.
And there's some stuff I don't tackle alone. I got to go to Geek and Chief. Charles Liu, friend and colleague.
Great to see you.
So, you're a professor at CUNY, Staten Island,
That's
City
correct.
University of New York. We've got you here because you think long and hard and deep about predictions made in sci-fi. You probably have some predictions of your own. The accuracy of these predictions and what they might have looked like at the time and what they look like to us with the benefit of hindsight.
Where do we go for our predictions? The tried and trusted sources. We'll have a look at that. Are the people that are making these predictions or writing examples, are they in fact the influencers of the future that are based in the past? Or if we leave it alone, does the future take care of itself? We'll get into all the sort of philosophical thoughts about that. But first and foremost...
Do you mean if we didn't predict the future so that there was no groundwork for new ideas, would future still have a place to land? Would it still unfold?
Would still unfold, yeah.
So let's look to science. Let's look to science fiction as our go-tos for what our lives might well be back. I mean, I'll kick it off. The Jetsons. This was made in the early 60s, 1960s, but it's set in 2062. So it's not that far away from
100
where we
years in
sit.
the future was
Yeah,
when
but
it was
where we
set.
sit today, it's not that far. So you've got flying cars. There's a robot in every house.
Yes.
Are the Jetsons the most accurate prediction of the near future we have, or do we have to look in other places for accuracy?
So I found this recently. Was it the year 2020? I was looking for years predicted for the future that are already in our past. And in the Jetsons, I think George Jetson, you can triangulate based on certain script lines that he was born in the year 2020. So here's what I think they got wrong. They didn't understand that a robot can be anything that does something that you wouldn't otherwise do.
Right.
He's still flying his flying car. He doesn't push a button and say, take me to work, and have the car do the work, as we have today. So they missed the fact that a robot did not have to have any humanoid features. This is the same with Isaac Asimov's iRobot, which predates the Jetsons.
Yeah.
Okay? In iRobot, the robots are humanoid.
Yeah.
And that's not necessary because it assumes the human form is something you want to emulate. And there's a lot of stuff we don't do well. Yeah. Make a machine do it better. So all I'm saying is, I don't think they thought about a self-driving car, which is itself a form of robot.
If we look at the movies and generally You're thinking about major budgets for production. Yet things don't always work out. You take the 1982 Blade Runner movie, Harrison Ford, remember that?
Based on,
I don't know what it was
yes,
based on.
based on a novel by,
Do Androids Dream of Electric Sheep by
Yes.
Philip K. Dick.
yep.
Well, thank you.
And when did he write that? Well, early 50s, right? Wasn't
Quite
it?
early,
Yeah,
yes.
yeah.
So it was set in 2019. So much of it doesn't land true.
None of it.
I mean, we have hindsight, which obviously is perfect.
Right.
But you're thinking about their humanoid and their off-world.
The replicants,
Yes.
yeah.
Doesn't exist. Didn't
The
happen.
replicants, right? That's what
Yes.
they're called.
That's what they're called.
They
Did
were-
not happen.
So we're not off-world.
No.
We don't have perfectly humanoid replicants.
Right.
And the sun sometimes shines.
Right.
I have my issues with dystopian futures because it assumes that whatever the trend line is in a culture, in a civilization, that it continues to descend without anybody doing anything about it at any time.
Right.
Not the public, not the politicians, not the military, nothing. It just continues to descend and hits rock bottom, and then they make a movie out of it.
I have a very, very quick.
It can happen locally.
I have a very
but
quick
globally,
theory on why that happens,
What?
why they do it that way. Because most dystopian futures are a warning against authoritarianism,
Well said.
and that's why that's why it's like
authoritarians can take it down the
that's
toilet.
right, and that's why it's like that's why they're always written that way.
Here's an interesting
Go on.
thing that happened in Blade Runner that we're kind of doing today.
All right.
All right. Do you remember the scene, very tense scene, where one of the replicants who's trying to pass as human is getting interviewed by someone whose task it is to identify the replicants who are no longer presenting themselves as replicants. And the replicants are so good that they have to go through a series of questions where they're testing the dilation of his eyes and his emotional reactions to certain situations. And there's a point where he's like he can't react in a way a human being would or would be expected to. My point is today, when people show me stuff written by ChatGPT, I'm analyzing that. If they don't tell me that, I'm analyzing it for, is there a human emotion in here that's authentic? Or is this replicated by something that thinks it can be human? I'm doing the same thing.
Yes.
Right? Yeah.
You are conducting the Turing test in real time.
But a better, a really deep
more
version.
discerning version
A more
of it.
discerning version.
Yeah.
Yeah.
Tell me
Yeah.
about the Turing test. Tell everybody.
Turing, the
Alan
famous
Turing?
guy,
Yes.
right, who helped create computers and so forth, he
Alan
said,
Turing, yeah.
yes, it would be important for us to figure out whether or not a machine has become truly intelligent by seeing if you can tell the difference between the responses of a machine and the responses of a human being.
Without seeing who's behind the curtain.
Right. And from there, you develop all the details, right? The Turing test as a general idea became specific about, like, for example, the things you're talking about, right, Neil? Analyzing text or analyzing responses like in Blade Runner. And so, in a sense, it was a predictive strategy to try to figure out whether something is what you think it is or
Is
whether
this not a
it's
test
something
more for not so
simulation.
much intelligence as consciousness?
It depends.
Turing obviously did not call it the Turing test.
Correct.
Do you know what he called it?
I do not remember.
Did you ever know?
I might have.
He called it.
I'm not intelligent enough.
He called it the imitation game. Hence
The name of the movie.
the title of the movie,
That makes-
which profiled his life
That's awesome.
with Keira Knightley
Benedict Cumberbatch.
and Benedict Cumberbatch.
So where else do we go? I mean, there are series like historically The Twilight Zone.
Absolutely.
And that
Rod
piques,
Serling.
that piques our interest.
The Outer Limits.
and
Don't
the
forget
outer limits, and we
Limits.
move through into more recently the Black Mirror.
Yeah. What's his name? Charlie
Brooker.
Charlie Brooker, who is brilliant.
So just to contrast the two,
Go ahead.
I think they both leave you emotionally spent and disturbed at the end.
And they're
if,
also
if,
both
if you
very-
go to the Twilight Zone in its day, and you look at sort of the disturbing stories that it told, and it didn't always have a happy ending.
Yeah.
And-
Is
and
this not the Ray Bradbury kind of school of thought? I need you to think.
Yes, and if you look at Rod Serling comment on his show, he said, look, well, at the end of the day, we're just selling soap, all right? So how do you sell soap in a way that people don't feel offended or whatever? And he says, if you set it in a fictionalized world where that's clearly not your world, then you can tell stories that people say, oh, that's just happening in that world. And later on, they pause and say, wait a minute, that was me, or that was my friend or my neighbor, or that's how I behaved. And so he was a storyteller par excellence in that genre. And especially, like I said, the disturbing feature of so many of those. And you fast forward to Black Mirror, which has an authentic science fiction future
Always.
foundation to it. Yes.
But
highlight what that future is, because some people might not know.
the future is this.
Black Mirror is a Netflix series.
Yeah, I believe it's on Netflix.
It's third season, the fourth season.
But
yeah.
the future is highly technologically driven. It's driven, everything is driven by technology. But the stories are about how we respond to the technological advancements. It's really never about the technology itself.
Very good.
It's always about our human nature and how it is affected by the technology.
And one thing that they do, which is just only a little out of reach in our imaginings, is in that future, which prevails in almost all episodes, because they share the same universe, right? Like the news that's on the TV is the same news casters that you see in multiple. So they're in the same world.
Right.
What they all have in common is that the human mind is accessible.
Right.
In the way hard drives are accessible.
Exactly.
And
often meshed in the way
right.
the way hard drives are
so if
connected.
you go into someone's head, rewind an event,
Right.
experience what they saw, see what they see through their eyes,
Right.
pull it back out, manipulate it.
Right.
That's a whole frontier of storytelling that's been unplumbed.
But when you think about it, it's a frontier of storytelling, but it is also a different facet of reality, because the way you experience something, even though we experience the exact same thing, is totally different from the way I experience it. And so what he does is he blurs the lines between individual realities, collective realities, and a technologically measured reality, which is brilliant, because I can look around this room and I'm seeing everything as it is seen through the
Chuck filter.
my filter, but I'm also seeing it through human eyes, as opposed to like the eyes of an eagle or an owl. I'm also
Or Geordie.
or Geordie, right?
LaForge.
And that's where I was. The next where I was going. But what I can't do is see it through the eyes of like an infrared meter. So all those realities exist at the same time, though.
Yes.
And that's what makes them so brilliant. I love.
So the idea that you
Love
can
it.
download your brain and put it on a computer, everyone's talking about that.
Yeah.
Black Mirror makes it real.
Yeah, and it's scary when you see.
It's scary to
what
see
he does.
and you see the nefarious ways people.
Well, the way they manipulate it in the way that really
It's
explores the darker side of our human nature. One of my favorite episodes is there's a guy, and he thinks that he's been in some kind of accident, and he's in a log cabin, and another guy shows up, and he's just like, hey, man, and he's like kind of nursing him back to health. He thinks he's been injured, and then he gets him to admit that he murdered his family or some crazy thing that he did. Wow. Only to find out that he was in a simulation and he was under interrogation by the police.
Oh, wow.
And then what they did afterwards was they punished him by leaving him in the simulation for a simulated 100 years, so that he would come out of his prison sentence thinking that he had been in prison for 100 years, when really he had only been in prison for whatever the time dilation mentally was for him. Maybe it had been a year.
So do we all think this is our future?
No. The reason I don't think this thing will work is simply because we are assuming that intelligence and perceptions and so forth can be so fully controlled that we can't tell the difference between a reality and what is not real. We already know that our brains can be fooled.
Right.
We already know that. So technology is not going to change anything in that respect unless we allow it to happen. And so I don't think that adding technology here, never mind the idea of whether or not our intelligence is actually digitizable, right? If it's a quantum situation, then you can never pass qubits and digitize as something called the no cloning theorem that makes that very difficult. The no cloning theorem is just one of many different pieces of quantum computing, sort of like the laws of quantum computing, the same way that Asimov had laws of robotics.
Okay.
Right? This particular one, the no cloning theorem, means that if you have a quantum bit of information,
All right.
you can't just make as many copies of it as you'd like. You can't make copies. So
Got
like
you.
us, we can digitize a photograph,
Right.
taking little pixels,
Exactly.
and then make each pixel exactly the same as another pixel on a
Absolutely.
hard drive or
Right.
a USB stick or something, and then you get an exact copy of the previous picture.
Absolutely.
Right. No cloning theorem says that for quantum information, you can't do that. So anytime you have some
and
quantum
why
thing-
wouldn't you be able to do that with a qubit as opposed to bits and bytes, which we're able to do
right.
it with?
As soon as you read a qubit, it is destroyed.
Can you only capture a freeze frame of that, your consciousness at a certain time? Because if you were to do it 5 minutes afterwards, it would potentially be different.
That
than
is
to
one
what Chuck said.
consequence of this no cloning idea.
Interesting.
Right? You can know what you are this very moment,
Right.
but you cannot know what is the next moment,
What
and
you
the
are in
moment
5
after that,
minutes.
and the moment after that.
Oh my God.
That's right.
If we're thinking about our future, if we're thinking about getting on and thinking about 50, 100, so many years in advance,
Yes.
what you describe in Starry Messenger is the exponential growth of our lives, our inventions, our ideas.
In our understandings, yes.
Right. So, and then you sort of frame it in a 30-year gap.
Yes.
I'm just wondering, and we'll return to exponential growth because I need to know how far away we are from being vertical on the graph. But if you took someone from 1995 and brought them to 2025, would they be completely out of sorts with the way we are today?
Yeah, let me tell you why that is definitely the case.
All right.
Okay, they would not know how to function. All right, little things like you sit them at a restaurant and say, "Where's the menu?" Oh, here's the QR code. They barely have an email address because those were on the rise beginning in the 1990s for the general public. The idea that you would have self-driving electric cars just on the road with no driver. If you walk around LA, these cars are just all over the place. Okay. And what role the smartphone has played in our lives, beginning from 2007 onward.
Yeah.
The idea that you can walk and talk to someone with something smaller than the size of a pack of cigarettes. What I'm describing is how the way we currently live and take it for granted will be wholly foreign and exotic and unfamiliar to someone transported from 1995.
Respectfully and with love, I disagree completely.
Because of 95 to 2025, or just in general, a 30-year interval?
No, it's specifically for 1995 to 2025 because we had Star Trek. We already saw what could be. We have Jules Verne. We had H.G. Wells. We had Lucian from the 2nd century A.D. He was a guy from sort of the Greek area of the world, which at that time was fertile with culture and imagination and so forth.
About when was this?
About the 2nd century AD.
Okay.
Oh, you know who else was the 2nd century? I don't know if they had
Ptolemy.
Ptolemy.
Okay.
He wrote
Yes.
Almagest.
I do not think
AD
it was a
150.
coincidence. That's
Because
the period
that's
of time.
laying out the universe.
All of the people that Charles has named there, they're historic.
Yes.
Wait. Lucian is not the name. That's the name of the
Lucian
piece?
is the name of the person who is credited with writing a science fiction novel called A True Story.
Wow.
Yes, Voyagers are on a boat and they are caught in a storm and they wind up on the moon. And at the moon, there are creatures who don't look like humans, but they're engaged in a great war. These are the kinds of things that have been imagined for a long, long time. And I don't think that anyone in 95 showing up in 2025 would go, "Oh my gosh, people are talking into a box." And they'll say, "Oh, wait, that happened in Star Trek. Okay, how does this work?" And they just tap, tap, tap. And because everything was built for humans by humans, they would be able to adapt
Instead
almost
of by
immediately.
aliens. Right.
Right, almost immediately because of the commonalities of humans from 1995 to 2025.
Okay, so now let's take it back to, and let's forget 2nd century AD,
Sure.
which is a time of enlightenment.
Yes.
Let's go to a time of darkness.
Uh-oh.
All right, the Dark Ages, where we're consumed by superstition, and everything is squelched in terms of any enlightenment.
First of all, we should understand that Dark Ages was a term coined by European historians.
True.
In fact, historians who claim that Rome fell in the year AD 476 did not take into account what we know to be true, that other people ran that area known as the Roman Empire in many different ways for centuries thereafter. And then there was the Holy Roman Empire that happened starting at 800 with Charlemagne. Meanwhile, there was an Eastern Empire that was based at Constantinople. So our sense of what history is also makes us think about predicting the past. What has been framed for us as the Dark Ages was actually a period of great innovation, and people were thinking about a lot of things, but not necessarily in Europe, in the Arabic-speaking world.
Okay, so if we use the imagination of these authors, these filmmakers, and then we kind of replicate some of the things that they came up, so we follow, we have sliding doors, we first saw them in Star Trek. Are they shaping the future from their position in the past? And we follow that.
Great idea. Great point. Here's my thought on this. We make predictions all the time. Probably there are 1,000 predictions about the future that are in the literature or just around on newspapers or even written down by people from 100 years ago. As Yogi Berra said, it's hard to make predictions, especially about the future, right? But if you make 1,000 predictions, one of them will come true. And we're looking backwards, right?
You cherry pick the few that came true.
And if the future shows up with sliding doors, you go back and go, hey remember that people?
Sliding doors,
we don't talk about anybody who predicted doors would go up and down or that doors would swirl out, but they exist, you know? So somebody probably did that, even though Star Trek as a show itself didn't have doors that swirled out. There are ways to do this that we have all thought of. They just didn't dominate our society for whatever reason.
Okay. All right, let's go to your 2050 predictions.
Quickly, to put this in context, in the book I describe a prediction in 1900 made for the year 2000. And in the year 1900, steamships were setting records across the ocean. Railroads crossed the continents. And so in this, for the year 2000, they had a steamship coming out of the ocean with railroad wheels flipped down. It goes straight onto a railroad track.
Onto a railroad track.
Also, how were people getting around? Through lighter than air
balloons,
dirigibles, blimps, this sort of thing. So they imagined in the year 2000, everyone would have their own personal balloons. So there are these balloons that wrap under in your armpit. It shows them sort of walking on water, kept buoyant by these balloons.
Marvelous.
And it's like, okay,
because that's the extent of their imagination. Couldn't go much farther than what was available.
There. That's kind of it. Okay.
What was available.
Amazing.
All right. One of your predictions, the space program becomes a space industry.
Already happened.
Funded not by taxpayers' dollars, but by space tourism and other projects.
That part didn't happen.
Prices are not going to drop low enough for people to want to go into space just for the heck of it.
Not for 30 years?
Not for 30 years. Unfortunately, you're watching the prices now, extrapolating outward into the future. You just don't see that pattern happening because right now what's happening is that space is still controlled by
countries,
governments that are willing to subsidize private corporations. Once those subsidies are removed,
doesn't every country on Earth have a same equity in the space?
You would hope so. But at the moment, as with any other parts of the world,
Charles, the dawn of flight, it was very expensive. Very few people was on a plane. If you flew on a plane, that was like the news of the cocktail party that you attended. And then now everybody can fly because the plane, we figured out how to make it cheap.
The plane was and always was, from the very beginning in 1903, a private enterprise activity. Space has, since its beginning, been a governmental activity.
Okay, that's missing some information. So the rapid development of flight between 1910 and 1930
was funded by World War I.
So you had government investments in
the advancement of aviation,
an advancement of aviation, and the government wanted to deliver mail by plane.
Right.
The birth of airmail. And so the government said, we're going to give a contract to whoever can outbid whoever else. And you do it, and you win the contract. I said, I want the contract. So I make my plane better because I can carry more for the same amount of money that yours does. Now I win the contract back from you. And this continues until somebody says, hey, instead of sacks of mail, I can carry sacks of people. And then that was the birth of commercial aviation, driven by the government's interest in you making a better airplane.
But it made money. And when we tried to do that with the space shuttle, we didn't make money.
So
until money is made, that track will not start.
And your sentence had the word until in it. Fine. I'm saying by 2050, the until will happen within there.
I do not think so.
Okay, that's what it is.
So here's what I think. In response to both of you,
Yeah.
what's going to happen is there's a lot of money floating around in space. And if we can mine what's out there instead of destroying the Earth to bring back all these precious rare Earths they wouldn't be rare Earths, they'd be rare space
minerals.
Rare space.
Yeah.
If we can bring that back, what happens is to get there, it's going to propel the advancement so fast.
Like a gold rush.
Yeah. That space tourism will be a natural byproduct.
Byproduct.
That's what I
So
believe.
not the target, but the byproduct.
Not the target.
Happens so often.
Right.
I want to read to you, we don't have time for this, but I'm going to do it anyway. I want to read to you a letter that I own,
All right.
written December 19th, 1918. This is to Mr. Alan Hawley, president of the Aero Club of America,
Then I know who wrote this.
Madison Avenue. Dear Mr. Hawley, many thanks for your very nice telegram remembering the 15th anniversary of our first flight at Kitty Hawk.
Whoa.
Although Wilbur, as well as myself, would have preferred to see the aeroplane developed more along peaceful lines, yet I believe that its use in this great war will give encouragement for its use in other ways. Signed, sincerely yours, Orville. Wright.
Yeah.
Look at that.
Yeah.
And in war, take the high ground, and they took it to another level, pun intended. Right, let's take another look. Self-driving electric cars, you go there, and I don't think that's
That's in there. Yeah.
That's not a limb that's going to be breaking. There are
There people who say that it'll never happen or whatever. People like driving, and we already have HOV lanes.
Right.
If you say you can only go in that if it's a self-driving car,
Right.
and the self-driving cars are going 120 miles an hour, 3 car lengths between each other because they have instant reflexes.
There are cars being made right now that don't have steering wheels, so we are going to live in a
Right. And I think
driverless car
that'll happen
society at one
faster
point.
than most people.
Agree.
Yes.
Yeah.
Do you agree or not?
I think that self-driving vehicles will be as prevalent as public transportation is today.
Right.
Good.
There will still be private transportation for which drivers will still be
Absolutely.
necessary.
And listen, you'll drive on the back roads and stuff like that. You'll be able to drive your car, okay? But one day...
Wait. At some point, they'll become like horses.
Yeah.
Okay? You can still ride your horse. Your horse is at the stables.
Right. You go get your horse and you drive and you ride.
Right. So now your car is at the
At the
track.
garage, at the track.
No, it's a special place where people
Well, that's what I mean, back roads.
who still want to drive their car, they go there and they drive their car.
Here's when it's going to happen. At some point, you have to make the cars talk to one another and the road itself talk to the car.
road.
Of course.
And at that
course.
point, you won't be allowed to
Right.
drive on the road.
You want to switch lanes, it tells the other cars, I'm switching
Exactly,
lanes, and they
exactly.
open up for
Right.
you. Half all the accidents happen that way.
But that-
you don't see who's in your blind spot.
But building that infrastructure into the highways and byways is going to be so expensive.
Yes. And there are still millions of square miles of North America where there isn't high-speed internet. So you got to remember that these are very regional solutions right now. We can extrapolate on what's going to happen in New York City, but the driving from Laramie, Wyoming to Fargo, North Dakota is not likely to be the same as driving
there's
from
no literal
LA
mapping.
Sunset Boulevard
Okay, in
to
1915,
LA.
many of those
Compton.
farmers still had horse-drawn tractors. Yes. But I'm talking about...
We're talking about the entire world. You're going to have
We're
an
talking about the
area.
Eisenhower freeway system, highway system in the United States.
Right.
It's going to be limited to certain areas.
I'm afraid
okay.
so.
Neuroscience will advance so far we understand the human minds well enough that mental illness will be cured. You've also gone into developing antiviral serum and cures cancer. Do
Yeah.
we feel that?
Yeah,
Some cancers,
some.
yes. Absolutely.
So with the neuroscience,
Science, yeah.
which is still kind of in its infancy, so
It
I have
is.
very high expectations for it. Psychologists hate it when I say this, but I mean it with love, that to me,
psychology is to neuroscience what alchemy is to chemistry. For months and months and months trying to cure their illness, the neuroscientists said, where is it? Oh, it's a nip tuck right here. There's a neurosynaptic thing there. And they nip and tuck, and you're done and you're out, and no one is on the street crazy. There's no insane asylums.
Is this where we get to implants? That just bypasses.
That's a great point.
The fractured
I don't know if it's surgery or implants or that are removable, then you go back to your original
All right,
state.
so let's look at AI. Let's look at the influence AI will have in the world of medicine. Is this now us getting to a more vertical line on the exponential
the
growth?
line always looks vertical when you're at that end of the exponential. It always looks vertical to you. Like all the advances happen just in recent years. But I want to get to the AI point. To the extent that can help with medicines, I think one of my predictions was we have medicines that, this is not some new prediction. I'm just echoing what's already been floating around, but I'm putting a timestamp on it, that medicine will be tuned to your genetic profile so that there are zero side effects.
Yes, you did make that.
Yes, and if we know why is it that you break out in hives and you don't, ingesting the same chemical, there's something different about your genetic profile or your hormonal profile. We will know that, understand it, so that side effects will be a thing of the past. That's one of the predictions.
You do make that prediction. I get it. It's in there.
Yes. I think what will happen is that we'll be able to control behaviors very well by 2050.
Right.
But we still won't be able to cure the diseases by 2050.
You
There's a lot to do.
You think eventually, just not by 2050?
Yes.
Okay.
It's an issue of when. In a quarter century, we'll be able to help everybody who have behavioral problems solve their behaviors. But that doesn't necessarily mean we'll have solved their diseases. And that is what I would like to see.
So that means they'll be living with the disease controlled by some medication or implant rather than have it removed from them entirely.
That's my opinion.
Good.
Is it
I'd
safe
like
to say that going forward into the future, that changes will happen even quicker?
That is the nature of being on an exponential. That's my point.
Yeah.
That there's no doubt. If you look at the pace of patents, the pace of research papers, the doubling times are, which is how you know you're on an exponential, they've been consistent over the decades. So what that means is in a few years, there'll be double the number of research papers on a subject in a field than has appeared up until that point. That's how you know you're on an exponential.
And the caveat is sometimes the exponentials turn over. There's a period of exponential growth followed by a leveling off.
Right.
For example, the human population. Thomas Malthus, a couple hundred years ago, predicted that if you use exponential growth, soon there will be so many people in the world that there will be not enough food production ever. But now we know that our predictions, and here's one that we could test in 30 years. 30 years from now, the exponential growth of the human population will turn over. We're going to top out worldwide around 10 billion
that's about right.
and stop.
Yeah, but you gave the wrong.
Actually start falling, as it has in many places.
People have already made those predictions.
Hold on. You put a cart in front of a horse there.
Oh,
okay. Malthus is wrong, not because our exponential growth of the population will level off at 10 billion. He's wrong because we applied science to farming, so that now we are producing more food on less land with fewer farmers than ever before. That's why he was wrong. He did not imagine that farm production would ever become more efficient or more voluminous than it was at the time. And he was just doing a linear extrapolation against the population of the planet. We are awash in food. Anyone who is starving in the world...
How much of our food goes to waste?
A third of it or something. I saw the numbers. So anyone who's starving, it's not because the world doesn't have food to feed them. There's some geopolitical circumstance that prevents it.
Give me each of you one final prediction about something that you would like us to know about.
See, so here's my prediction for it's going to go...
And don't confuse what you want to be true from what will likely be true.
This is my honest assessment, not my desire.
Good.
Okay? That we are at a global tipping point with respect to democracy globally. And it's either going to be that people want to govern themselves through democratic processes, or that we descend into authoritarianism worldwide. And if we do, getting back is going to take so many generations, none of us will be here to see it.
Gary, a prediction.
That we find the desire to fully engage with climate change because the knock-on effect has influence on so many global societies. We're suffering from climate migration, we're suffering from rising sea levels, and if we can bring the desire to challenge and tackle that positively, I think that will be something we can all look to as the positive step.
I so hope you're right.
All right, what's your best prediction?
That within 25 years there will be a professional sport played in orbit.
All right, we got to wrap this up. Charles, Chuck, Gary, thanks for
Pleasure.
Always.
This has been StarTalk Special Edition. Neil deGrasse Tyson, as always, bidding you to keep looking up.